Very good day to you all. My name is S.Adebayo. We shall be discussing the waves under physics today. Waves. We were taught something like this before, but we're going to take a kind of revision or preview over some of things that has to do with waves. And so under this, we talk about mechanical waves. What are the graphical representation of waves? What are the terms that we use in wave? What is the relationship between the frequency, time, and the wavelength? And what we are going to solve little issues or little problems on this. So the topic is waves today. And first thing is production of mechanical wave. When we say mechanical wave, a wave is a disturbance which travels through a medium and transfer energy from one point to another without causing any permanent displacement of that medium itself. This particular formula or this particular definition is a very important definition in physics. A wave is a disturbance which travels through a medium and transfer energy from one point to another without causing any permanent displacement of the medium itself. Have you ever imagined, or maybe you have walked about when we are very small, we try to take one handkerchief. We take the handkerchief, we try to roll it around, and we try to be using it to eat the second person or your friend. What you are doing is that you are transferring wave from the handkerchief to the person. So whenever you are transferring a kind of disturbance through a particular medium and the medium itself is not having a kind of displacement, or the medium itself is not causing permanent displacement, what you have experienced is the wave. Now look at when you get to a very still water. Let me just give another instance of that. A water that is still, when you get to let's say a river, is still, is calm. When you put a very big stone, put it inside the water, you see the waves that roll away from the water, that spot, and fade away. That means you cause a kind of disturbance to the calmness of the water. And you see, by the time you do this, you see that waves, that the coily things that flows away from that. So if you drop out, I think this is exactly what it is explained. If you drop a stone into a water in a basin or swimming pool, ripples or waves will be seen spreading outwards from the source of the disturbance as the waves generated spread out. So they transfer energy from one point to other without the water moving in the direction of the ripples. And that's the diagram you are seeing there. That's the diagram of a wave. And so by the time you draw, look at the stone, that's at the center, black thing. By the time you draw, you see the ripple of water to the right and to the right. That is the source of the disturbance. So there will be ripple. And the wave goes right to the and the left. Water did not go right. That's why we say it does not cause a permanent disturbance. The water is not going to the right nor the left, but the wave, that wave goes to the right, or ripple goes to the right or the left. Another thing is what I explained to you is like the handkerchief. That's like a spring. Or you must have seen that by the time you hold a particular long cloth, like a bedspread, you hold it at one end and you just try to push, you try to take it up and scroll it down. You see that you generate or a rope. When by the time you have a long rope, a long thick rope, you just take it at one end and you just spread. You apply a force. You can see you experience something like that, like the one in the second diagram here. You experience something like this. You can see the person holding the rope at one end. It tries to create a kind of wave. It moved when you move the rope creates a kind of curly wave or disturbance to the end that is being tied. That's another example of a wave that has been propagated. Now, the wave can also be produced when one ties one end of a rope to a wall. I think that's exactly what the diagram explained there. When you hold the other end and you make it move up, down rapidly. So alternatively, you get a long string and place both ends. Look at this diagram there. Look at this diagram. When you have a long string and you now place the both ends fixed. One end is fixed, second end is fixed. Plug the string, or when you plug is that you strike from up down. You will see that a wave will also be generated downward or upward, and it will spread towards the right rather and towards the left by the time you struck the spring, because the two ends are already fixed. Now, the second thing I want to discuss here is the terms that are used in wave. These are mechanical wave anyway, and we are going to still talk about what a mechanical wave is all about anyway. That is when we talk about the wave that requires a material medium, because any mechanical wave is typically a wave that requires a material medium. We are going to also be discussing later the electrical wave, because electromagnetic wave. The electromagnetic wave is a wave that does not require material medium. It travels inside a vacuum or free space. So those are the two main types of classification of wave. We have a mechanical wave, a wave that requires material medium. We have electromagnetic wave, which is the wave that do not require material medium. Look at the diagram here. A wave is somehow sinusoidal in nature. When I say sinusoidal, it's like a sine graph. A sine graph is a graph that is sinusoidal. It's go start from the origin, move up, get down in the diagram, like the diagram you are seeing there. Now, when you say a wave, look at that graph. You can see that there's a peak P of the wave. Look at the P and Q. These P and Q are referred to as the peak, or we call them the crest of the wave. And the one beside the lambda here is the bottom. Look at the one beside lambda here. We call them the trough. We are going to explain that. And look at A. Now, using this diagram, let us look at this diagram very well, and let us talk about each of the terms. The first one is crest. A crest is the region of maximum displacement of particles of the medium. Maximum displacement of particles of the medium. Look at this. In this diagram now, what is the maximum displacement? The P, because it's going P downward, back. It also go to Q downward. So it's going up and down. Don't forget, a wave is more or less a vibration. A wave is a vibration. It goes to flow. That's why we call it oscillatory motion. A wave is still an oscillatory motion because it's a motion that repeats itself after a particular or after a kind of interval. So a wave is a vibratory motion. It's an oscillatory motion to flow. So you can see it goes up to P, goes down back to where the lambda is, go up back to Q, goes down. So it's coming up, off, on, off, on, off. So that's exactly what we call it vibration. And that's exactly what happens when we have vibration. So the crest is the region of maximum displacement up. So when we have a the trough, look at the B now, trough is the region of maximum downward displacement. So maximum upward displacement, like from 0 to P, is the crest. But when you go from 0 to down to around where the lambda is reaching, that is the trough, the bottom. That's the coffee bottom. That is the trough. That's the maximum downward displacement, because it's going up, it gets to a particular peak, it goes back down, gets to a particular peak down. So that the peak down is what we call trough. The phase is the distance, or let's say two particles of a wave are said to be in phase when they are in same vertical distance from their mean position and are moving in the same direction. Look at this now. Any object in life, any object in the wave rather, are said to be in phase when they are at the same vertical distance from their mean position. P and Q now are in phase. You can see, because they are in P is at the trough and Q is at the trough. The amplitude is the length. Now this one does not talk about the length. I said that the maximum displacement from the mean position, the starting position, to the vertical is the trough. Sorry, is the crest, and the one downward is the trough. Now the length, look at the arrow I put there. The length, look at the arrow here. The length from that main position to the trough or the length of the mean position to the crest. It might be the length from the zero to trough, or that length is the amplitude of that wave. And that's why we say amplitude is the maximum displacement of the particles as measured from the mean position. The period is a time taken by a particle to complete one cycle of oscillation. A cycle, look at now, a cycle is a lambda. Look at this diagram, look at lambda. P to Q is a lambda. From the position 0 to where I put the dot down is also a lambda. A kind of complete circle. Let's look at this diagram very well. It starts from O, goes back, pass through P, gets down back, and you can see that by the time you get to the second arrow beside the Q there, it resembles another one. It resembles the one. It's the peak, another peak. So from one peak to the one peak, we can say we have a wavelength. That is a complete circle. This wave is now repeating what he has done before. Because from one peak to another peak, that's a cycle. It can be from one trough to another trough. Because at times you can have a kind of two trough. So from one trough to another trough, that is also a cycle. Or from one particular position to a corresponding position of that in another phase, in another line. When we have point A now, the point A in the next phase in the another line is the wavelength. So that's why we say wavelength is a distance or a length between a distance to complete a cycle. So a cycle can be from trough to trough, or from crest to crest, or from any two successive or corresponding distances in phase. Any two corresponding distances in phase. The length is the wavelength. So we now said that the period, I think I've said about the period, is time taken to complete one cycle. So the unit of the unit is seconds. I said the distance for one cycle is the wavelength, but the time to complete that distance is the period t, and it's measured in seconds. It can also be defined as the time taken for the wave to cover one wavelength. You can see. So the time taken for a particular wave to cover one wavelength, that's from P to Q now, is a wavelength. You can see another lambda. Lambda is because the wavelength is represented by lambda. You can see that the wavelength is then then the number, or is a complete cycle distance, and the time to complete that one cycle distance is the wave. Is the period, which is measured in seconds. So the period now is the time over number of oscillations. Look at the formula that I want to take note here. The period t is the time divided by the number of oscillations. That's the difference between the period and normal time. It's not just a time. If we have 3 oscillations in 1 minute, the period is that 1 minute by 60, which is in seconds, over the number of oscillations. So the period t is time over numbers of oscillation. Now, another thing I want you to know is frequency. The frequency is defined as the number of cycles that wave makes in 1 second. Number of cycles per second is what we call the frequency. Number of cycles means per second. Please, the spelling of this cycle should be CYCLES, cycle. So the number of cycles made in a second is the frequency. That's why frequency is in N over T, and it is measured in hertz. Wavelength, I think I've talked about this before, the distance between two successive crests, you can see, or two successive troughs in phase. It can be defined as the distance covered by the wave after completing a cycle. It measures in meters. It is measured in meters. I told you it's a length. So it is measured in meters, the length. It is measured in meters. So then the wavelength, lambda, is equals, generally velocity is distance over time. That is what we have learned so far. But in the wave now, the distance that a wave moves now, according to the diagram, is the wavelength. That is the distance from one trough to trough, or one crest to crest, is the wavelength. And the time is now the period. So if you now want to use that idea of velocity equals to time over distance over time, and we want to bring that idea back to the wave, you see that the velocity there now becomes wavelength over period. Period is the time in the wave now, and wavelength is the distance in the waveform. So that's why we have v equals to lambda over t. V equals to lambda over t. And since the frequency, frequency is 1 over period. We have learned this one under the simple harmonic motion, that f equals to 1 over t, or t equals to 1 over f. By the time you put frequency in, or you substitute the fact that we have velocity equals to lambda over t, so the frequency is 1 over t, put this one as t in the formula. Look at the formula. This formula, v equals to lambda over t. Put t as a formula. That means t is also 1 over f. By the time you substitute t equals to 1 over f in the formula v equals to lambda over t, what you get is v equals to lambda f, or v equals to f lambda. Let's look at some examples on the usage of this formula I just did. You can see that I have nothing less than FGH about 6, to I think F is 5, 6, 7, 8. 8 parameters I've defined. I've defined what's a crest, what's a trough, what's a phase, what's an amplitude A, what is the period, what's the frequency, what's the wavelength, and what is the velocity of the wave. And there are some that have formulas there that we need to intimate ourselves with the formula. The period t is time over n, and the frequency is also number of oscillation over time. The wavelength and the velocity is also related in such a way that the velocity is equal to wavelength over time, or the velocity equals to the frequency by the wavelength. So because either you say v equals to lambda over period, that is when we are given period and lambda, or v equals to f lambda, that's when we are given the frequency over frequency and lambda. And don't forget that the frequency is equal to 1 over period. Now look at this question. A wave travels a distance of 100 meters in 5 seconds. The distance between successive crests of the wave is 25 meters. Calculate the frequency. Look at that question. A wave travels a distance of 100 meters in 5 seconds. That is a linear distance. So that is v. 100 meters in 5 seconds. So I've been able to give us distance and the time. That is, and we can get our velocity from there, which is the meter, so the distance over time. And they said distance between successive crests. A distance between any two successive crests or any two successive curves is the wavelength, according to the definition. So the question, we should calculate the frequency. Look at the parameters listed here. You can see distance equals 100 meters according to the question. Time is 5 seconds. Lambda is 25 meters and 25 centimeters rather. 25 centimeters is not the centimeter is not the SI unit for distance. Whether you have wavelength or we have distance, the distance or wavelength is a distance, and it must always be in the SI unit of distance, which is in meters. So that's why we have to convert this 25 centimeters to meters. That is by dividing it by 100, and we have 0.25 meters. So velocity is there for distance over time, and the distance is 100 and time is 5 seconds. So we get the velocity to be 20 meters per second there. We now use the formula v equals to f lambda, because the question says we should find the frequency, and we already know the velocity now according to what we calculated, and the lambda has been gotten by dividing it by 25 divided by 100 and get 0.25. So by the time we now make f, the sort of formula, we have f equals to v over lambda. That is f equals to 20 over 0.25, which is 80 hours. I told you that the unit of frequency is hours, or we can say it is circle per second. Some scenario or some conditions whereby they give you circles per second as unit of hours. Don't forget, 1 hour is 1 circles per second. I told you that frequency is the number of circles made in 1 second. So frequency here is 80 hours or 80 circles per second. Let's look at the second example here. A radio station broadcasts a frequency of 200 hertz. A radio station broadcasts a frequency of 200 hertz. If the speed of the wave is 3.0 times 10 to the power 8, calculate the period and the wavelength of the wave. Now, they gave us a frequency. 200 kilohertz. 200 kilohertz. And kilo means 1,000. No, that is 200,000 hertz. Because we have to convert it. That is a kilo. So it actually means frequency is 200 kilohertz, which is 200,000 hours. You can see that in the other solution. We are given velocity in meter per second, which is 3.0 times 10 to the power 8 meter per second. Because if you calculate the period here, you can see we have V and F. You can easily calculate the period because we are given it. You don't forget F period is 1 over F, or F is 1 over T. So by the time you have 1 over 200,000, we have that one to be 5 times 10 to the power minus 6 seconds. So we get the period. So the question says we should find the period. Sorry, we find the wavelength as well. That is the period. The period is 5 times 10 to the power minus 6 seconds. Don't forget this period is in seconds. Then the second aspect of the question is the wavelength. By using the formula V equals to F lambda, the wavelength made it so the formula we have the lambda equals to V over F. And then we have V to be 3 times 10 to the power 8 divided by the F, which F is the 2 times 10 to the power 5, or 200,000. And by the time we have that to be 1.5 times 10 to the power 3 meters. That's the wavelength. That's the wavelength. So that's another example. We have another example here, which is the last example I'm going to talk about today's class. A vibration source has a frequency of 500 Hz, producing a source whose velocity in here is 330 meters per second. So we are given velocity to be 330 and frequency to be 500. Determine the distance which the sound travels when the source completes 100 vibrations. Don't forget 100 vibrations. A vibration is a complete cycle. Don't forget that. A vibration is a period, or is a kind of movement to through. That is a complete cycle. Now they say we should calculate the distance which the sound travels when the source has made one vibration. The first thing is that we were given the frequency to be 500 and we were given the number of vibration to be 100. So there we can get the time for using the formula frequency equals to number of vibration or number of oscillation over time. So that time can be gotten from there, and that's why we have the time to be 0.2 seconds. So this is the time for the wave to complete 100 vibration. That's the time. So time we have gotten there is the time to complete that 100 vibration. So by time now, the question now is we shall find distance, and we have been given the velocity 330. We have known the time. We have given velocity. So don't forget that velocity is equal to distance over time. So that's why we have the 330, which is velocity equal to the distance over time. And that's the distance we asked of us to find. So the distance there becomes 66.0 meters. And we can also use an alternative method that I show you here. You can look at that frequency equals to 500 hours or 500 cycles per second. So if the source makes 500 cycles per second, then it will make 100 over 500 seconds in 100 cycles. So we get the time there, and we can say the speed equals to distance over time, and then we can say that distance equals to speed and times time, and that is 330 times 0.2, which is 66 meters. So that is exactly what the alternative method says. If you want to use the alternative method, now there is an evaluation that I want you to look at here. And there is an assignment that I'm going to at least ask you generally on the weekend. The first one is, what is wave? Define wave and represents its motion by a diagram. Calculate the frequency of a wave if its period is 0.25. 5 cycles are formed in 2 seconds. What's the period of the wave? There are questions that will also be put towards or directed towards you by weekend, because we are going to be tested on this wave, the basic ones. We are going to continue from this aspect in our next wave class. We are going to continue with complex situations about how we tackle some problems that are more complex about waves in our next class. I hope you have gained one or two things in this class. And there's a weekend assignment there that I want you to read towards the next class. You read the transverse and longitudinal wave. You read the transverse and longitudinal wave. There's nothing bad if you try and check your textbook for this and what is the wave motion. So by weekend I will be testing your knowledge about what you have learned so far in this topic. And so far I want you to also try to put your textbook beside you and try to use this as a guide to study waves under your textbook. Thank you very much and stay blessed. Meet you in the next class.